you like to see Mona Lisa smile like a witch? Or would you like the girl with the pearl earring wink and smile? Well, Google has just dropped a video generation model that's capable of doing all of it for you. Though it's primarily a text-to-video model, it's able to do much more than that. Given a reference image with a prompt, it can stylize your videos by copying the style of a reference image to your videos. You can even edit your videos with just a single prompt. The model is Lumiere. It's even able to animate objects with its user-specified region in an image, a technique called cinemagraphs. When it comes to in painting, Lumiere is even able to reason about a completely missing object, such as a cake in this example. It all boils down to a diffusion model with the novel Space-Time UNet architecture. It's a customization of the UNet architecture to solve the problem of temporal consistency, which is quite prevalent in video generation models. So, what is temporal consistency or inconsistency? We all know that videos are a sequence of images. So let's take a sequence of images shown in the top row. If we narrow down just to one line in the image, which is indicated by this green line going from left to right, we need to see a smooth transition in the pixel values between images in the sequence. If the transition is smooth, then we won't see a jumping effect while we are watching the video. For example, if we take stable video diffusion and see this video of an astronaut walking on the moon, we can see that his hands just disappear between frames. Or in other words, the temporal consistency between frames is lacking. This kind of temporal inconsistency between time and the intensity in the x direction can be plotted as the xt slice, and if there is temporal inconsistency, it's clearly highlighted in this plot. So Lumiere addresses this problem by introducing a space-time diffusion model and a modified UNet architecture present in the diffusion model. Before looking into the details, let's start with the typical pipeline of text-to-video generation models. These pipelines sample every fifth frame as the key frame from the input video sequence and train a base model that can generate these keyframes at a resolution as low as 128 by 128 with just 3 frames per second. Then, a temporal super resolution is used to increase the frame rate by predicting the intermediate frames. So the frame rate now becomes 16 frames per second. The spatial resolution of these frames are then increased to 1024 by 1024 by a spatial super resolution network, which finally leads to our generated video. The base model used in this framework is usually a diffusion model, which in turn has a UNet inside it. The proposed pipeline by Lumiere, on the other hand, processes all the frames at once without dropping frames or without picking the keyframes. In order to cope with the computational cost of processing all the frames, the architecture of the base diffusion model is modified to come up with the Space-Time UNet architecture, or STUnet. As STUnet deals with all the input frames, the need for temporal super resolution, or TSR, is eliminated. So the pipeline still has the spatial super resolution, or SSR, but the novelty is the introduction of MultiDiffusion. Let's quickly review the UNet before looking into the Space-Time UNet, or STUnet. Now the input to the UNet is a 3-dimensional image with width, height, and channel RGB. After every double convolution stage of the UNet, we apply max pooling to downsample or reduce the spatial dimension of the features. This spatial dimension reduction step is indicated by the red arrows. Similarly, during the decoder stage, There are up convolutions to increase or upsample the resolution back to the size of the input. When it comes to videos, we have an additional dimension in the input, which is time. So Space-Time UNet proposes to downsample and upsample the video not only in the spatial dimension but also in the dimension of time. This idea of downsampling in the temporal dimension is the main contribution of the Lumiere paper. For resizing, they use 3D pooling instead of 2D pooling, as the input now has an additional dimension t. Like me, you may be surprised by the simplicity of the idea. The authors themselves have mentioned, surprisingly, this design choice has been overlooked by previous text-to-video models, which follow the convention to include only spatial down and upsampling operations in the architecture and maintain a fixed temporal resolution across the network. Let's get to some of the nuances of the implementation. The authors use a factorized convolution, which was introduced in this paper titled Video Diffusion Models. The idea is to change each 2D convolution into a space-only 3D convolution, for instance, by changing each 3x3 convolution into a 1x3x3 convolution. And for the attention, after each spatial attention block, we introduce a temporal attention block that performs attention over the first axis and treats the spatial axis as a batch axis. With those two changes, the factorized convolution blocks are added to the pre-trained model and only the additional layers are trained with the pre-trained layers being fixed. The second novelty of the paper is the MultiDiffusion, introduced during the spatial super resolution. Now, if we take the video generation model before Lumiere, the spatial super resolution model took a sequence of frames. In fact, we had a cascade of super resolution models, but the sequences were not overlapping. For example, the first 8 frames and the next 8 frames taken as input by the SSR module are typically separate without any overlap. But when it comes to Lumiere, the first 8 frames and the second 8 frames have an overlap of 2 frames. By doing this, the spatial super resolution seems to achieve smooth transition between the temporal segments. And this is what is referred to as MultiDiffusion in the paper. Coupling the two proposed techniques along with the absence of cascaded diffusion model, which is prevalent in prior architectures such as image and video, leads to quite a few varied applications. For example, the model is able to convert text from videos, such as an astronaut walking on planet Mars making a detour around his base, or a dog driving a car wearing funny sunglasses. The model is also able to convert images to videos along with a prompt saying a girl winking and smiling. It's able to stylize generations with a reference image and a prompt such as a bear dancing. Talking of cinemagraphs, it's able to animate fire or steam. It's even able to edit dresses that people are wearing with just a single prompt. To evaluate the model quantitatively, the model was run through a user study where the users compared the results of the proposed model against some state-of-the-art models such as Pika, Xeroscope, or Stable Video Diffusion, and the results clearly indicate that the users preferred the Lumiere model, both in case of text-to-video and image-to-video. So to conclude, other than all the promotional video stunts such as Smiling Mona Lisa, the contribution of this paper is fairly simple. Put in one line, the paper introduces downsampling of the temporal channel. This, coupled with MultiDiffusion, which is nothing but having overlapping frames fed into the super resolution model, generates high fidelity videos that are temporally consistent. What I would have liked to see is some ablation studies in the paper showing the results with and without the multi-diffusion process. Well, that brings us to the end of this video. The next time someone talks to you about Lumiere, you know what to say in one line. So I hope that provides some insight into the Lumiere model. I will see you in my next video. Until then, take care.